Okay, so hopefully this one behaves itself. So I'm going to be providing some options of projections for marine heat waves, sea surface temperatures, and some ocean acidification variables. And so I'm going to very briefly describe how they're defined and why do we even care about them in terms of marine heat waves. And then, as I said, give some options for potential marine heat wave projections. And I'd really like, obviously, feedback on whether this is a sort of information that you would find useful. And the same for the ocean acidification variables. I'll give a brief overview, but also, and then some examples of what could be provided. And then again, yes, it'd be great to have just some feedback on whether that's useful or you wanted to do something else. So marine heat wave research has really sort of taken off, I guess, in the last sort of, I don't know, probably 6 or 8 years in terms of there's been a lot of research on them. And because of that, a group of research scientists, international scientists, came together because they wanted to produce a standard definition of marine heat waves, so that everybody, all the research on it and all the information on it is referring to the same definition and the same thing. So they came together, and now marine heat waves are defined as a discrete, prolonged, anomalously warm water event which lasts for 5 or more days with temperatures warmer than the 90th percentile relative to climatology. And this is shown in this this sort of illustration here. We've got time and temperature, and the blue line here is the climatology, so the average. The green line is this 90% threshold value, and that accounts for seasonal differences as it's uniquely calculated for each calendar day. And then in this illustration, the black line is a sort of pretend set of observational data, so sea surface temperature data. And so it's only defined as a marine heat wave when it passes that 90th percentile threshold. And these aren't, can you see my cursor? Hopefully you can see my cursor. These aren't counted as marine heat waves because they don't last for more than 5 days. And so in terms of this one, so these, you get these heat spikes, but they wouldn't count any of the marine heat wave statistics. And so you get this sort of pattern, and then they have a specific end date when they go below that 90th percentile. So as well as having this definition for marine heat waves that everybody uses now, there's also a standard definition in terms of the categories, and so like the intensity or the strength of the marine heat waves. And so there's 4 categories, and they go from, sorry, I'm just going to push this one down here. Sorry, my screen's in the way there. There we go. They go from moderate, strong, severe, or extreme. And I won't go into sort of how they're calculated, but they're the difference really in multiples of the difference between the percentile, the 90th percentile, in terms of each category. So that's the sort of statistics that we use in terms of these 4 marine heat wave categories. So with this one, again, it's just showing as an example. This is the climatology, this is the observed sea surface temperature, and you're able to describe, sort of durations in each of the categories, what the peak of the marine heat wave event, what sort of category that was in. And that can be useful, as you'll see in a second. And then finally, the other sort of standard set of things that those sort of scientists came together. There was the standard definition of marine heat waves, the standard categories. And there's also a standard set of metrics that's typically used to examine and quantify. So this includes looking at the sea surface temperature anomaly. So each of these row panels is for a different marine heat wave event. Looking at the sea surface temperature anomaly, so how much warmer than average it was. Looking at these strength and durations of these marine heat waves, and then looking at these sort of statistics in terms of how long they've lasted and what the trends are over time, the maximum intensity. In terms of why we care about them, there's three main reasons. First of all, they're really widespread, occur globally in all of the oceans and coastal seas. They often have wide-ranging and sometimes devastating impacts on a variety of marine species, key habitats, including corals, seagrass, kelp, and also fisheries and aquaculture species such as abalone, lobster, crabs. And the pictures in the bottom there are actually showing some fish and invertebrate kills that happened in Fiji and Vanuatu at the same time as the February 2016 marine heatwave. And it's also responsible for coral bleaching. And the other picture there shows bleaching in Samoa in 2015. And the other reason we care about them is that globally, trends in marine heat wave frequency, intensity, and duration have increased over the last 4 decades, which are shown in this panel on the right here, which this is frequency, intensity, duration, and globally average SST. And that climate projections indicate this trend is set to continue for many regions, including the Pacific. So I'm not going to dwell, these are historic analyses I've done already, and I won't dwell too much on the historic analyses because today is really about sort of the projections and what projections are useful for you. But the sorts of things I've done in terms of looking at these area averaged marine heat wave statistics. And for now, I've done it for Espiritu Santo and Fate. And you can look at these sort of durations and cumulative intensities. And you can see that the longest durations and greatest cumulative intensity have occurred in the last sort of 15 to 20 years. So this goes from 1982 to 2020. And the other bit of historic analysis is quite useful is looking at the annual mean sea surface temperature anomalies from 1982 to 2019 for Espiritu Santo and Afate. And basically the red bars are basically warmer than average sea surface temperature years. And you can see that there's been more warmer than average years really in the last sort of 20 years than the previous 20 years. And this bottom plot then shows for each year the annual number of marine heat wave days in each category. So the yellow is moderate marine heat wave and the orange is strong. And so you can see that for both locations, most marine heat waves have been in the moderate category with a few in the strong. And this is useful for bearing in mind when we then look at projections and sort of putting those projections into context. So the projections for marine heat waves have used 18 CMIP-6 models. There's been a paper last year looking at sort of comparisons between CMIP-6 and CMIP-5. It was Australian based, but actually showed that for marine heatwave metrics, CMIP-6 models performed slightly better than those in CMIP-5. CMIP-6, you'll see when I'm showing the plots of different emission scenarios, they don't use RCP, they use SSP, and that stands for Shared Socioeconomic Pathways, and it's sort of the equivalent of, well, it is the emission pathways, but it's the equivalent of the RCPs. And so the 126 and 585 result in similar radiative forcing levels by the end of the century as the CMIP-5 predecessors. So you can kind of think of them relative to 2.6 and 8.5, which you might be more familiar with. So I'm going to show 3 types of projections data, and like I said, it'd be great to get excuse me, some feedback as to whether these are useful. So I'll be showing projected annual number of days in each of the marine heatwave categories, projected maximum category attained, and then the area average time series. So I'll show some examples of these now. Oh, and sorry. And so I say here area average time series. And I just wanted to make a quick note on that in terms of regional averaging. So the plot on the left here shows the long-term mean sea surface temperature. It's over almost 40 years, at 82 to 2019. And the lines here are the partitions that Dewi is using with her projections, which were based on things like rainfall and air temperature and other metrics that were important to her. And obviously I wanted to do some regional averaging using metrics that are relative to the marine projections. And so I've based it on the sea surface temperature contours. These are like I said, the long-term average sea surface temperatures. For now, I've split them into north, central, and south, which each have a sea surface temperature range of about 1.5 degrees. And they sort of actually roughly align with Daly's sort of regional average. That's more sort of, yeah, it's not done on purpose, but I guess it's quite useful, I suppose, that they do probably quite align. So now just some examples of the sorts of projections we can give. So what this shows is the multi-model means. That's the mean of all 18 models. It's the projected annual mean number of marine heat wave days by 2030 in the top row here, and 2050 in the bottom. And it's for the low emission scenarios in the left panel and the high emission scenarios on the right panel. And each of these smaller plots is the, like I said, the projected mean number of marine heat wave days in each category. So this is the moderate category, strong, severe, and extreme. And there's a couple of interesting things I think that this shows. Is first of all, when you think back to the historical analyses that we did, that show that most of the marine heat waves were moderate or strong, and you can see really that there's a large increase under the very high emission scenario. The other interesting thing, I think, is the difference between the two emission scenarios, and that actually they increased by a whole category. So what I mean by that is, if you look at 2050, the 2050, the SSP 1.126 projects around 25 to 75 strong marine heat waves, whereas for the higher emission scenario, that same number is actually projected in the more intense category, the severe category. Similarly, the lower emission scenario projects around 100 to 175 strong marine heat waves. Oh, sorry, I'm looking at the wrong one. Sorry, my cursor's at the wrong one. The higher emission scenario projects around 100 to 175 strong marine heat waves, with 100 extra days in the moderate category projected under the high emission scenario compared to the lower one. So this sort of information could be really useful. Some other considerations. So this now is showing the projected annual number of marine heat wave days in the moderate category by 2050 under the high emission scenarios, but it's actually showing it for each model. And you'll see, as is typical with the climate models, there's some variability in terms of projections. And one question we might want to think about is whether we just provide the multi-model mean, or sort of best, worst, and mean case, rather than allow it sort of providing all of the models, which can vary by around 100 days in some of these instances. So now the second type of data we could provide is actually looking at the maximum category reached over the 20-year period. So for here, it is centered on 2010 as an example. And on the left here, we've got an observation project called OISST. And this is looking at a 20-year period in each of these spatial regions. What was the highest intensity marine heat wave that was experienced? And then we can also do this by looking at the CMIP6 models. And this is useful in terms of perhaps looking at places that have experienced stronger marine heat waves. And also we can then look at that to look at future projections. And so each of these, sorry, I'm just going to go back up, but each of these colors refers to a category of marine heat wave. And it's quite easy to see then where actually we experience these more extreme marine heat waves. And as I say, we can do that also for the future projections. And then the final type of projection we could provide is these time series of either sea surface temperatures and marine heat wave days. And so here on the big plot on the left is for the whole sort of Vanuatu region. And we're showing the projected sea surface temperature up until the end of the century. the different colours are for different emission scenarios. Now this is using CMIP5 data now for the sea surface temperatures. So we're using the red for the high emission scenario, and the purple is the low emission scenario, 2.6. The bold line for each of them is the median value, and then we're also showing the range. And the black line is sorry, a regionally averaged sea surface temperature and the observed sea surface temperature, which is useful in terms of looking at where we're tracking. And then we can do that for these 3 different regions in terms of the north region, the central, or the south. And so that can be another type that we could provide. So I'll just go into the ocean acidification projections as well, and just a bit of a reminder of what that is. So ocean acidification is a term given to changing ocean chemistry due to the oceanic uptake of atmospheric carbon dioxide, and which results in reductions in pH and aragonite or calcite saturation states. And these are forms of calcium carbonate used by organisms such as corals and shellfish. And this altered seawater chemistry can negatively affect corals and shellfish and even fish through impact on growth, survival, recruitment, and food-web relationships. It's difficult to predict critical thresholds for different corals, different fish, different shellfish, because it's certainly with the shellfish, even closely related species can respond differently. And also most experiments have been conducted in relatively short-term laboratory conditions. And some research is showing adaptive capacity and others not. But generally for corals, it's understood that aragonite saturation states less than 3 are likely to make it difficult for sustained coral growth. And I guess it's just worth pointing out that ocean acidification, those effects are often exacerbated by a warming ocean and multiple other stresses. And certainly a lot of the laboratory studies have shown that the outcome is a lot worse when those experimental conditions for carbon dioxide also include increased ocean temperatures. So in terms of the oceanification related projections available, we're using CMIP5 models. And again, there's 3 types of projections that we can provide, which is the projected change for pH and aragonite saturation state, projected future values, and then the area average time series for each of the 3 regions. And just a reminder, I suppose, that the projected changes that we provide are for surface open ocean projections and don't account for the numerous local processes that modify ocean chemistry, especially on reefs. And again, local observations will be very useful. So this is the sort of thing that we can provide. So this is now showing a projected change in aragonite saturation state by the year 2050. The top panel is the low emission scenario, RCP 2.6. The middle is RCP 4.5, and the bottom is the high emission scenario. And by showing the sort of the different percentiles, shows the sort of best and worst case for each of the emissions and this time period. So in this case, this is the best case with the least change, and in this situation, this is the worst case with the most change. And then we can also do something similar in looking at best and worst cases for each of the different time periods. So now this is for 2030, 2050, 2070, and 2090, the low emission scenario and the high. And again, it gives us this range of change and allows us to look at this sort of best and worst case. And then we also do that for pH as well, which I'm not showing here, but that is another thing for pH. And then again, we can also show this as a time series. So as I showed before, this is now for aragonite saturation state for the whole of Vanuatu, and then the north, central, and south on the right. And again, we're showing this median and also the range of projections over time. And so that might be also something that's useful. And then this is the same one for pH. So I'll leave it there. I'm happy